In this video, I am going to solve a GCE A-level chemistry MCQ June 2020. I will be solving MCQ June 2020 for A-levels chemistry. But before we continue with our topic today, please support us by liking this video and subscribe to our channel. Do not forget to hit the notification bell. Welcome back. Thank you once more for taking your time to subscribe to our channel. We will be starting with question number 1. Question number 1 iterates: which one of the following processes is exothermic? There are 4 reactions there. Reaction A is enthalpy of atomization of oxygen. Of course, that one is endothermic. Energy is needed to atomize it to its gaseous state. Reaction B is the second electron affinity of oxygen. Of course, energy is needed to bind the second electron to the first. Reaction C is the first electron affinity. That one is exothermic. Reaction D. Reaction D, that is the first ionization energy. Excuse me. The first ionization energy. Of course, it is endothermic. So, from all this reaction, the only reaction that is exothermic is reaction C. That is the first electron affinity of oxygen. Reaction C is the answer. Reaction C is the answer. Question number 2. Question number 2. Gunpowder burns with a lilac, that is purple flame. The metal in gunpowder that causes this flame color is A. Sodium, B. Calcium, C. Potassium, D. Calcium. Of course, you know it is only potassium that will give you a lilac color. Potassium is the metal that will give a lilac flame color. So the answer is C. The answer is C. Question number 3. Which of the elements below exhibits the inert paired effect? First of all, what is an inert paired effect? An inert paired effect, in our previous question paper, I said this is the ability of the outermost s electron. The ability of the outermost s electron to remain paired and do not take part in bonding. In other words, you can say the reluctant of the outermost s electron to take part in chemical bonding. So The outermost electron is remain paired, and to unpair it will require a lot of energy. For that purpose, it doesn't take part in chemical reaction, and it will exhibit an inert paired effect. Going through question 3, we have sulfur, we have sulfur, we have lead, we have sodium, and we have magnesium. From all these, it is only lead. It is only lead that has 6s electrons. It exhibits an inert paired effect because of the outermost 6s electrons that are paired. So our answer for the question number 3 is B. Is B. Let's go to question number 4. Question number 4 has to do with organic reactions. Give the name of the reaction that occurs when ethene reacts with aqueous bromine. Aqueous bromine. For ethene is an unsaturated hydrocarbon. Reacting with aqueous bromine, bromine will be acting as an electrophile. Remember, an electrophile is electron pair acceptor. An electrophile is an electron pair acceptor. In this case, ethene being an unsaturated hydrocarbon, the pi electrons will donate, the pi electron will donate a pair of electron to bromine. The pi electron will donate a pair, the pi electron in the double bond will donate a pair of electron to bromine. And bromine will be acting as an electrophile. Remember, I said an electrophile is an electron pair acceptor. So in that case, it is not going to be electrophilic substitution. It is not going to be nucleophilic addition. It is not going to be nucleophilic substitution. It is going to be electrophilic addition, because we are adding bromine across the double bond. So our answer for number 4 is A. Electrophilic addition. Question number 5. Choose the apparatus that can be used to easily monitor the rate of reaction between manganate 7 ion and ethane diurate ion. Remember that manganate 7 ion is purple in color. It acts like an indicator. When you are using manganate 7 ion in a reaction, you don't need an indicator again, especially in titration. You don't need an indicator again, because itself is acting as an indicator. So in such a reaction, we will not need a dilatometer, we will not need a calorimeter, we will not need a polarimeter. What we will need is a colorimeter. A colorimeter to monitor when we will reach our endpoint, because during this reaction, the manganate 7 ion is reduced to manganese 2, while the ethane diurate ion is oxidized to carbon dioxide. So we will need but a colorimeter. So our answer here is D. Question number 6. It has to do with some calculations. That calculation and titration. What volume and concentration of sulfuric acid will be needed to exactly neutralize 20 cm cube of 0.3 molar sodium hydroxide. Let's go to our calculation. The first thing when you have a titration calculation like this is to write uh, um, the chemical equation, a balanced chemical equation. So we have sodium hydroxide and sulfuric acid to give sodium sulfate and water. Okay, we have been given one of it, which is we have been given for um, we have been given for sodium hydroxide. We have been given the volume for sodium hydroxide, and we have also been given the concentration for sodium hydroxide. Remember, there is a formula. We say concentration is equals to mole divided by by volume in dm cube. We have to convert the volume to dm cube. But in order to have the number of moles, we rearrange this equation. In order to have the number of moles, we rearrange this equation. The number of moles now will be concentration times the volume in dm cube. So now we want to calculate for sodium hydroxide. Sodium hydroxide is 0.3 molar, and the volume is 20 cm cube. 20 divided by 1000 is 0.02. So now to have the number of moles of sodium hydroxide, that is the OH, sodium hydroxide, the OH, let me just say the OH, it will be concentration times the volume. So the concentration is 0.3 times the volume. The volume in dm cube, 20 divided by 1000 is 0.02. And what we will be having will be 0.006 moles. That is for sodium hydroxide. For the acid, for sulfuric acid, remember 2 moles of sodium hydroxide are reacting with 1 mole of sulfuric acid. Now that we have got the moles of sulfuric acid, the moles of sodium now that we have got the moles of sodium hydroxide, the moles of sulfuric acid will be, we have to divide it by what? By 2. So we'll divide the moles of the of sodium hydroxide by 2 to have the one for acid. So the moles of the acid will be what? Will be 0.006, which is the mole of sodium hydroxide, divided by 2 will give the moles of will give us the moles of the acid. That will be the moles of the acid. Now we have said, now we want to take by simple proportion. By simple proportion, since we said 0.03 molar are in 20 cm cube. So we now say if 0.006 moles of the alkali, that is the sodium hydroxide, are in 20 cm cube, therefore the moles of the acid 0.003 of H plus, that is the acid, would be in X. So we do that calculation. If we do that calculation, we will have 0.003 times 20 divided by 0.006. It will be 10 cm cube. Now the volume of the acid will be 10 cm cube. That is not the concentration. We have got the volume. To have the concentration of the acid, remember there is a formula again. I said to have the concentration, we will have moles divided by volume in dm cube. Okay, now we have the moles of the acid to be 0.003. We have the volume of the acid to be 10 cm cube. So what we need to do is divide the number of moles by 10 divided by 1000. So then we get it here. So the concentration of the acid will be 0.003 divided by 10 divided by 1000. That is, we want to bring it to dm cube. Now rearranging it, we will have 0.003 times 1000 divided by 10. Our concentration for the acid, for sulfuric acid, will be 0.3 molar. Our concentration for sulfuric acid will be 0.3 molar. So now we now say the acid has 10 cm cube and 0.3 molar. Let's go to our answer column and see it there. 10 cm cube and 0.3 molar. 10 cm cube and 0.3 molar. 10 cm cube. Okay, it is D. D is 10 cm cube of 0.3 molar sulfuric acid. So this is D is our right answer. Now let's go to question number 7. Question number 7 has to do with how to distinguish between organic compounds. Now, which of the reagents below can best be used to distinguish between propan-1-ol and propan-2-ol? Remember, propan-1-ol is propan-1-ol. This is a primary alcohol. Then propan-2-ol. This is a secondary alcohol. Okay, all are alcohols. Let's use the reagents. The reagent neutral ion 3 chloride. We cannot use it to distinguish it. Concentrated sulfuric acid, we will only use it for dehydration. And acidified potassium manganate 7, we will only use it for oxidation. All of them will undergo oxidation. But A, which is alkaline aqueous iodine. Alkaline aqueous iodine. This reagent is used to identify secondary alcohol. This reagent is used to identify secondary alcohol, especially propan, for example, propan-2-ol. Again, this reagent is also used to identify any compound that has a methyl group on the same carbon that bears the functional group. Because the end product of this reaction, the reaction of propan-2-ol with this, the end product will be a triiodomethane, yellow precipitate of triiodomethane. So it is only A. The reagent A will give us a yellow precipitate of triiodomethane. So this reagent is used as an iodoform or a triiodomethane test. It is used as an iodoform test, or what we call a triiodomethane test. And when it reacts with propan-2-ol, we will have a triiodomethane, a yellow precipitate of triiodomethane. So A is the right answer. Question number 8. It has to do with the first ionization energy. Question number 8 has to do with the first ionization energy. Here, you will see that in this reaction, you will see that the graph below is part of a plot of a log of ionization energy against number of electrons removed from element X. In which group of the periodic table is element X found? Okay, when you see such a question involving number of electrons removed on the x-axis and log of the first ionization energy on the y-axis, what you need to do is look the trend. You have to look at the trend of the graph. Look at the trend of the graph. On this trend here, you will see that the first electron that has been removed, then the second electron that has been removed. After the first and the second electron, of course, the first and the second ionization energy. This is the first electron here. This is the second electron here. You see that there's no big difference between them. If you look at the first ionization energy, there's no big difference between them. But when you are about to remove the third electron here, this green here, there is a big jump. There is a big hike. There is a big jump here, indicating that The third electron is coming but from another energy level. It is coming but from another energy level. The third electron, the fourth electron, and other electrons to be removed. They are coming but from the same energy level. But the first and the second electrons are from another energy level. So indicating that the first two electrons come but from an element belonging to group 2 of the periodic table. The first two electrons removed are coming but from an element belonging to group 2 of the periodic table. In that case, we will say it belongs to group 2. So let's go to our question column. In which group of the periodic table is element X found? It belongs to group 2. So our answer is B. Our answer is B. Question number 8, our answer is B. Let's go to question number 9. Question number 9, it has to do with decays. It has to do with decays. The number and the type of particles emitted in radioactive decays. A radioactive decay of Mn to V, that is 57 to 49, and 25 atomic number to 23, are A, 2 alpha particles, B, 1 alpha particle and 1 beta particle, C, 2 alpha particle and 1 beta particle, and D, 2 alpha particle and 2 beta particle. Okay, let's see how the decay is going. Assuming this is the element here, this is the element here, Mn with atomic mass of 57, with atomic number of 25. It undergoes a radioactive decay to 49, atomic mass of 49 and atomic number of 23. In this case, we are from all calculation, we have seen that 8 and 2 have been lost, and we are looking at our alpha decay. 2 alpha decay have been emitted. 2 alpha decay have been emitted. If 2 alpha decay were emitted, we will only have this. We will only have 8 and 4. But the atomic number has reduced to 2, implying that a beta decay, 2 beta decay have also been emitted. So we have 2 alpha decays, 2 alpha particles. We have 2 alpha particles and 2 beta decay resulting in this. So if we go back to our answer column, we will see that 2 alpha particles and 2 beta particles have been lost. In that case, our answer D is the right answer for us. Now, let's go again to naming of organic compounds. That is question number 10. We have an organic compound here, given the IUPAC name of the following. Okay, give the IUPAC name of the following. This is a structure that has been given. We have 1, 2, 3, 4. There are 4 carbon atoms here. 1, 2, 3, 4. 4 carbon atoms. The 4 carbon atoms, there is an ethyl group here. The ethyl group here is the molecular formula that has been compressed. The molecular formula that has been compressed, it is C2H5. Remember, an ethyl group is CH2, is a CH2. An ethyl group is a CH2 and a CH3. That is an ethyl group, but the molecular formula has been compressed to C2H5. So if we will add this here, the carbon chain is going to increase. Let me go there. Excuse me. Okay, so now we will have to write this formula. We have to write all this, the molecular formula that is here, that has been compressed here into CH2, CH3. Write it out clearly. This is what we are going to have. This is what we are going to have. We are going to have a CH2 here and a CH3. Now we have to number it because the naming of the of organic compound preference is given to the carbon chain having to the longest carbon chain. Let's number it 1, 2, 3, 4, 5, 5, 6. We have 6 carbon here because the carbon chain has increased. Now let's number this one with the one with 6 is hex. Is hex. In that case, it is hexane because it is an alkane. Let's number the one with green. 1, 2, 3, 4, 5. It is pent. It's 5. It's pent. In that case, it is pentane, since it is an alkane. Now let's see how we can number it. We can do the. We can give the naming now. Remember, there is a bromine. There is a bromine. Bromine is attached. We have to number using but the one in blue. We have to number using the one in blue because that is the one that is given preference. That is the longer chain. In that case, bromine is attached. Bromine and methyl group, they are attached to the third carbon. Now, according to the IUPAC system of nomenclature, priority is given by to halogens. So we will now give priority by to bromine first before going to the methyl group. So we will now say the position is 3. So we now say, in that case we will say 3 bromo. We will say 3 bromo. Then we now go to the methyl group. 3 methyl, 3 bromo, 3 methyl. Our parent name is hexane. 3 bromo, 3 methyl hexane. So if we go back to our compound 3 bromo, 3 methyl hexane, we will see that 3 I said it is 3 so I said it is 3 bromo. It is on the third carbon atom, 3 bromo, 3 methyl hexane. So now 3 bromo, 3 methyl, 3 bromo, 3 methyl hexane. Our answer is A. Our answer is A. Question number 10, our answer is A. 3 bromo, 3 methyl hexane. That will be our answer. Okay. Question number 11. Question number 11. Chlorine may be prepared in the laboratory from concentrated hydrochloric acid by heating it with A. Concentrated sulfuric acid. No. B. Manganese 4 oxide. Yeah. Sodium chloride crystals. No. Lead 2 oxide. Our answer is B. Question number 11, our answer is B. We can only prepare chlorine in the laboratory using the action of hydrochloric acid on concentrated hydrochloric acid on manganese 4 oxide. And this is how you can get it here. You can get the reaction here. A reaction of chlorine in the laboratory is like this. Let me show you how it works. Chlorine in the laboratory. we will have manganese. This is it. Manganese 4 oxide plus hydrochloric acid, concentrated hydrochloric acid. We will have manganese chloride, plus water. Water is produced. Water is produced plus chlorine. The chlorine is, that is the gas. The chlorine is produced. Let's balance our equation. We will have 2 here, 2 there, 2 here. Yes, we will have 4 here. So that is to produce chlorine in the laboratory. That is the equation to produce chlorine in the laboratory. Action of concentrated hydrochloric acid or manganese 4 oxide. So our answer here, our answer will be for number 11, our answer will be B. Okay, number 12. Number 12. Which one of the following element is most likely to have successive ionization energy in kilojoule per mole? Okay, we just treated ionization energy up there. We are going back again now. The figures have been given. Let's see. We have, I said when a question like this is being given, try to look at the figures, try to see the trend in the ionization energies. Try to see the trend in the ionization energies. Where there is a gap, where there's a big gap or a big jump, know that that one is from a different energy level, and from there you can start calculating whether it belongs to a particular element or a particular group of the periodic table. So let's go ahead with this question here. You have 7.86, 1,580, 3,000. There's not too much big gain there. 4,306. Now there's a big jump here. There's a big jump here. 1, 2, 3, 4. After 4 ionization energies, then there's a big jump at number 5, implying that number 5 is from number 5 and number 6 are from different energy level. So 1, 2, 3, 4, 4. So they are asking on which one of the following element is most likely to have successive ionization energy in kilojoule, like this one. So 1, 2, 3, 4. It should be a group 4 element. It should be a group 4 element because the fifth one is from another energy level. And the only group 4 element in this group, we have aluminum, magnesium, phosphorus, silicon. So it is D. It is D. Our answer here is D. It's only silicon that can have that. Then number 13. Number 13. Given the following data, enthalpy of formation of methane is this. Enthalpy for the graphite, atomization of graphite to carbon, gaseous carbon is 712, and atomization of hydrogen to gaseous hydrogen is 215. You have been given this. Then the bond energy in kilojoule per mole of carbon of CH bond in methane is given here. Okay, we need to calculate the bond energy. The average. We need to calculate the average bond energy for the carbon hydrogen bond in methane. So the first thing you do here is you need to draw an enthalpy cycle. Hesse's law. What is Hesse's law? Hesse's law is very, very important. Hesse's law is very, very important. So So using Hesse's law, we can draw this. This is how we can draw this. There is carbon. This is carbon here to atomization. This is hydrogen, atomization, enthalpy of formation of methane, and the reaction from this to this. We want to use this enthalpy cycle to find the average bond energy of CH bond. Let's do this. According to Hesse's law says the direct route is which one? The direct route is the one that we are leaving from the elements directly to their gaseous state, to the atoms, the elements right to the atoms, the gaseous atoms. That is the direct route, and the direct route will involve enthalpy of atomization of graphite and enthalpy of atomization of hydrogen. Then the indirect route will involve what? We have to go straight to the enthalpy of formation of methane, then the enthalpy of the reaction, and that is why it is indicated by the dotted line. So according to Hesse's law, in forming this equation, we have to say the direct route equals to the indirect route, and the direct route will do this to be enthalpy 2, and this one will be enthalpy 1. So let's do this. This is how we are doing it here. I can say direct route equals to indirect route. Direct route is enthalpy 1, and indirect route is enthalpy 2. This enthalpy 1, enthalpy 2, I have just put them there, but we are going to substitute them with the real values here. So enthalpy 1 is equal to what? Enthalpy 1 is enthalpy of formation of methane and the what? And enthalpy of reaction. This is it here. Enthalpy 1 is enthalpy of formation of methane and enthalpy of reaction. Then enthalpy 2, this is enthalpy 2 here. Enthalpy 2 is enthalpy of atomization of graphite and enthalpy of atomization of hydrogen. Remember, when we are doing the multiplication, we will have to multiply it by 4 moles of hydrogen atom. So enthalpy 2 will be enthalpy of atomization of graphite and enthalpy of atomization of hydrogen. Now we put everything. What we are looking for is the enthalpy of reaction. What we are looking for is this, because all the other values have been given. What we are looking for this enthalpy of reaction. So now we will look for the enthalpy of this will be the enthalpy of reaction. Rearranging this equation to have the enthalpy of reaction, we will say enthalpy of reaction will be what? Enthalpy of graphite plus enthalpy of atomization of hydrogen minus enthalpy of formation of this one, of the formation of enthalpy of formation of methane. So when we do like that and we substitute our values, if we substitute our values, the value for enthalpy for hydrogen was, for methane was for methane, the value was minus 775. Yeah, this is it here. So we will substitute this value here, minus 75, and the enthalpy of reaction will be plus 1649 kilojoule per mole. Okay, that is not the average. That is not the average bond energy for CH bond. So the next step number 2 will be what? We will draw our methane. We will draw our methane now and equate our methane to this reaction we have got here. So our methane here, how many CH bond are in methane? 1, 2, 3, 4. So we now say 4 CH bond in methane equals to that the value of that reaction. Then we now make CH bond the subject, and when we make CH bond the subject, we will divide 1649 by 4, and our value will be 412.25 kilojoule per mole, and that is when we have it, that will be our average bond energy for CH bond, 412, and that 412 will give us a certain value here. It's plus 412, of course. It's plus 412. It's plus 412. a plus 412, which is plus 412, and when we come here to our column of answers, our 412 will be B. Our answer for number 13 will be B. B will be our answer for question number 13. So we now proceed to question number. So once more, please, you have to draw your enthalpy cycle to find the average bond energy. It's very, very important. When you draw it, you now form an equation. We call it direct root equals to indirect root. That is according to Hesse's law. When you do it like that, you substitute the values. Substitute the values. The answer that you will get, you will now equate it to the number of CH bonds in methane. You now equate to the number of CH bond in methane, and then calculate. Now make CH bond the subject, and you have your value. And when you do it, you now come and tick your answer. Thank you. Now, question number 14. Which of the hydrates below will be hydrolyzed in water to give a basic solution? Hydrate. The hydrate hydrate is not methane. A basic has to do with a group 1 metal. Basic oxides, basic hydrates are dealing with especially group 1 metals. Are the basic ones in this group. So if we have something like lithium, we have something like sodium, have something like potassium, then we have preference should be given to it. So now our first answer is methane. It is not right. Our second answer is silicon hydroxide. It is not right. Our third answer is boron hydride. Is not right. The third one is sodium hydride. The right answer is D. The right answer is D for number 14, because there is sodium there. That is a basic solution. So we have a D there. Number 15, we have to go back again on how we can differentiate. Choose the organic compound from the list below. Choose the organic compound from the list below. That will give a yellow precipitate with alkaline aqueous iodine. We are back to this same question, this same similar question. I told you that aqueous alkaline iodine is used. This is a triiodomethane. This reagent is used in triiodomethane test. This reagent is used in iodoform tests. So we say this reagent alkaline aqueous iodine is used to identify. This is used to identify any compound that has a methyl group on the same compound, on the same carbon that bears the functional group. Let me just show you here. Let me just show you an example of it here. For instance, look here. I said any compound. That test, the iodoform test or the triiodomethane test, is used to identify any compound that has a methyl group. This compound has a methyl group. It has a methyl group. This methyl group is on the carbon atom that is bearing the functional group. So any compound that has a methyl group attached to the carbon atom that is bearing the functional group, it will identify it. For instance, this other one here, This is ethanol. Ethanol is at this is a methyl group. It is attached to this carbon atom bearing what? The functional group. This is a methyl group. It is attached to this is ethanol. It is attached to the carbon atom bearing the functional group, which is the OH group. This is an ethyl group, a methyl group. This methyl group is attached to the carbon atom bearing the functional group. In this case, we call this a methyl ketone. This is a methyl ketone. So that reagent is used to identify, once more, that reagent is used to identify any compound that has a methyl group on the same carbon atom bearing the functional group. So in this case, if we go back to our question, there, and the end product of it is always a yellow precipitate of triiodomethane. If we go back here, our question says, choose the organic compound from the list below that will give a yellow precipitate with this reagent. Okay, let's start from D. D, of course, there is a methyl group here, but the methyl group is not attached to another carbon bearing the functional group, so it is not good. The methyl group is not attached to another carbon bearing the functional group. Come here, we don't have any methyl group here attached to the carbon bearing the functional group. Come here, we don't have any methyl group. We have a methyl group here. The methyl group is attached but to oxygen. It's not attached to another carbon that is bearing the functional group. Let's come here to A. Okay, there is a methyl group here. This methyl group is attached to the carbon atom bearing the functional group. In this case, this is a methyl ketone. So this one is A will give a yellow precipitate with alkaline aqueous iodine. So we say A. A will give a yellow precipitate with alkaline aqueous iodine. So A is the right answer. And the value of the name we call it is a methyl ketone. And the real name of A is butan-2-one. Butan-2-one. 1, 2, 3, 4. Butan-2-one. So it's a ketone. So let's go to question number 16. Question number 16. Which of the following compounds will likely undergo a nucleophilic addition? Nucleophilic addition. What is a nucleophile? A nucleophile is we say electron. We said electrophiles are electron pair acceptor. On the other hand, nucleophiles are electron pair donors. They donate a pair of electrons. Nucleophiles are there to donate a pair of electrons. They are electron pair donors. So if they are electron pair donors, so they will only be going to centers where there is electron deficient centers. Electron deficient centers. It cannot go with ethene because ethene is electron rich. There is a high density cloud of electrons in ethene, the pi electrons. It can't go with ethene. It cannot go with bromoethane. It cannot go with benzene because only substitution that will go with the hydrogen on the benzene ring. But something that will undergo a nucleophilic addition is only ethanol. Ethanol is the only one that can undergo nucleophilic addition. Ethanol is the only compound that will undergo nucleophilic addition. Let me just show you how it goes. Let me show you how ethanol will undergo this. Okay, this is ethanol. When ethanol, for instance, react with hydrogen cyanide, the cyanide is going to be the cyanide ion will be acting as a nucleophile to donate a pair of electrons. So this is ethanol here. This is ethanol here. Now, because of the polarity between carbon and oxygen, you see it. This is the mechanism. Ethanol has a lone pair. Cyanide has a lone pair of electrons. The cyanide ion has a lone pair of electrons here to donate here. And when they are donating electrons here, because of this, there is a shift of this electron here to a pair of electron here. And this is what is formed. This is a complex, or this is the intermediate that is being formed. This intermediate, because of the lone pair of electron here, it will grab the hydrogen ion, and this will now result in what we call, this is an addition, it will now result in what we call 2-hydroxyl propane nitrile. This is 2-hydroxyl propane nitrile. So it is only ethanol that can undergo this nucleophilic addition. So our answer here will be only ethanol will undergo nucleophilic addition. So our answer for question number 16 is C. Question number 17 has to do with rates of chemical reaction and some calculations. The reaction fluorine plus chlorate to give fluorochlorate was shown to give the following results at 250 degree Kelvin. There were 3 experiments that were conducted. We have fluorine, the one for fluorine, concentration of fluorine, the concentration of chlorate, and the rate of reaction, rate of disappearance, the rate of disappearance. Okay, now the reaction is first order with respect to, okay, what we need to do is we need to calculate our order of reaction for fluorine and chlorate before coming to the answers. Okay, in order to calculate the order of reaction, one thing you must do is you must keep one concentration constant and use the concentration of the other one and the corresponding rate. For instance, if we want to calculate the rate with respect to fluorine, the order with respect to fluorine, we need to keep the chlorate constant. In this case, we are going to keep this constant. So we will be dealing with 0.20 divided by 0.10. 0.20 divided by 0.10 equals to what? 2.4 times 10 to the minus 3 divided by 1.2. This is how you can do it with respect to fluorine. With respect to fluorine, this is how we can do it. This is how we are doing the calculation. With respect to fluorine, this is how we are going to do it. Okay. With respect to fluorine, I said it is 0.20 divided by 0.10 to the power x equals, the rate is what? The rate is 2.4 times 10 to the minus 3 divided by 1.2. Let me go there again for you to better understand. When you keep this constant, when you keep the concentration for the chlorate constant, use only the values, the corresponding values that you are keeping constant on this side. For instance, I'm keeping the first one and the third one constant. I'm going to use this one. So it will be 0.20 divided by 0.10 equals to 2.4 times 10 to the minus 3 divided by 1.2 times 10 to the minus 3. When we do that, This is how we get our corresponding rate. When we do that, this is how we get it. We will divide it, we'll have 2. When we divide this by this, we'll have 2. Okay, this raised to the power x, all have the same basis, 2, 2. Now to the power x and to the power 1. Therefore, we now say x is equals to 1 because they have the same basis. So now go back and do your revision on basis, log and basis. So you now say 2, if this has 2 to the x and this is 2 to the 1, x be equals to what? X is equals to 1. And if the order of a reaction is 1, we call it a first order. If the order is equals to 1, we call it a first order. Why we use K? I decided to use K here because I decided to use but the rate, how to write the rate equation. Like here. Like in this case here. Because the rate will be equals to this to the x and this to the y. Okay, now let me go back again. So the order with fluorine is first order. Now let me go back again and calculate the order with respect to chlorate. The order with respect to chlorate will be, okay, I have to calculate this with respect to the chlorate. So it will be here will be, I have to keep fluorine constant. In order to keep chlorine constant, I have to do this constant. Okay, I am going to use only this. I have to do this constant. So in this case, I am going to use but only 0.04 divided by 0.1. I'm keeping this constant and I'm using only the corresponding one on the right. So 0.04 divided by 0.01 is equals to 4.8 times 10 to the minus 3 divided by 1.8 times 10 to the minus 3. Come here, you will see the same thing. Okay, the respect with this 0.04 divided by 0.1 to the power y, this is the y that we're talking of, then equals to 4.8 times 10 to the minus 3 divided by 1.2 times 10 to the minus 3. When we divide this by this, we will have 4 to the power y. When we divide this by this, we will have 4 to the power 1. We are, therefore, y, they have the same basis, y is equals to 1. If y is equals to 1, that is the order is equals to 1. We now say it is first order with respect to the chlorine. So it is first order. So all of them are first order, first order. It is first order with respect to fluorine and first order with respect to chlorine. So let's go back to our answer column and choose our right answer. All of them are first order, first order. So A, first order with respect to this and zero order, no. B, second order, no. C, first order with respect to this, first order with respect to fluorine and first order with respect to D. C is our right answer. C is our right answer. So C is our right answer. First order with respect to fluorine and first order with respect to this. So C is our right answer. C is our right answer. So that is our right answer. No, question number C is our right answer. Question number 18. Question number 18. When bromine is refluxed with potassium hydroxide in an alcoholic medium, compound Y is formed. Give the identity of Y. You know, when bromoethane is refluxed, it's a substitution reaction. It's a substitution reaction. When it is refluxed with potassium hydroxide, we call it ethanolic alcohol. We call it ethanolic sodium hydroxide or ethanolic potassium hydroxide. You can still call it potassium hydroxide in alcoholic medium or ethanolic potassium potassium hydroxide or ethanolic sodium hydroxide. Here we have been given potassium hydroxide in alcoholic medium. So it is alcohol that is usually formed. It is ethanol that is usually formed. So our answer is C. Question number 19. Question number 19. 19. From the principal oxidation state of sulfur, identify the oxidation state of a sulfur compound. A sulfur compound, which is essentially a reducing agent. Remember, a sulfur compound that is a reducing agent is a pollutant. We did it when we're doing environmental chemistry. Greenhouse, when we're doing about acid rain, we're talking of sulfur dioxide, other type of thing like that. Sulfur dioxide is a good example of a sulfur compound, which is a reducing agent, and at the same time, a pollutant. So sulfur dioxide. For instance, it would say sulfur dioxide X minus 4 X X minus 4 is equals to 0. X is equals to plus 4. So I will say that from the principal oxidation state of sulfur, identify the oxidation state of a sulfur compound, which is essentially a reducing agent. Sulfur dioxide is a reducing agent. So we will now say it is A. Question number 20. Consider the following two reactions. We have this reaction nitrogen plus nitrogen dioxide to give plus oxygen. That's combustion to give nitrogen dioxide is plus 88. Nitrogen again combustion. Again it gives the nitrogen. I think it's the nitrogen dioxide. To give plus 10. What will be the enthalpy change for the reaction this and that? Okay, Hesse's law is very, very important. Hesse's law is very, very important. I will take you back to Hesse's law, how you can do what we call enthalpy of combustion. Enthalpy of combustion of nitrogen. Enthalpy of combustion of nitrogen. Enthalpy of combustion of nitrogen. Look at the enthalpy of combustion of nitrogen. Okay, the enthalpy, if I draw using Hesse's law, we have reactants here, we have compounds that are being formed here, we have combustion products that are being formed here. Combustion products. Okay. Here, what you can do here is nitrogen plus the reaction has been given. This reaction can get back to this one. This reaction can get back to this one. This reaction can get back to this one. This reaction can get back, and then this one can get back to this one. Now, according to Hesse's law, the direct route is equals to the indirect route. This is the direct route from here. Nitrogen plus oxygen comes back to N2O4. This is the direct route. The indirect route is the one that comes from the reactant to the compound form, and from the compound form it comes back to a combustion product. And it is indicated by the dotted green line going around here. So according to Hesse's law, you should learn how to draw this. Look at your textbook, see how you can draw it. You always learn how to draw it, and by learning how to draw it, you will know if you are given a reaction, you know how to draw it and formulate an equation From here, we can formulate our equation. We can formulate our equation as direct root equals to indirect root. And the direct root is from where? It's from N2 nitrogen plus oxygen to give N2O2. This is the direct root. The indirect root is what? It is enthalpy 3 plus enthalpy 2. So direct root equals to indirect. We now say enthalpy 1 is equals to enthalpy 3 plus enthalpy 2. Remember, we have been asked to calculate by enthalpy 2. We will now make enthalpy 2 the subject. Okay. Direct equals to indirect. This is how you do it. We now make enthalpy 2 the subject. Enthalpy 2 now becomes enthalpy 1 minus enthalpy 3. Now, enthalpy 1 is what? Enthalpy 1 is from this, from nitrogen plus oxygen to this. The value is 10. It is given. It is clearly given. From nitrogen this to this, nitrogen plus this to this, it is 10. The value is 10. Then the enthalpy 3. Then enthalpy 3 is what? Enthalpy 3 is from here to NO2, and it is plus 88. The value is given. It is plus 88. So now, here, if we substitute our value, enthalpy 2 will now be equal to what? Plus 10 minus 88 will be equal to negative 78 kilojoule. And the negative 78 kilojoule, that is the value for enthalpy 2. Now, that is the value for enthalpy 2. That will be the value for enthalpy 2. Now, if I have to look for the value of enthalpy 2, negative 70, negative 78, what will be our answer? Negative 78 will be, the value will be C. The value will be C. So our answer for question number 20 will be C. It will be C, negative 78 kilojoule. Negative 78. That is our value for the answer for question number 20. Now, let's go now to question number 21. Question number 21. Question number 21 has to do with question number 21. It has to do with energy changes and activation energy, enthalpy changes, and activation energy. Okay. The following potential energy diagram is for the an uncatalyzed reaction. This is an uncatalyzed reaction. The energy change is 190 and activation energy is 160. The question reads, when a catalyst is used, the activation energy of when a catalyst is used, the activation energy of the forward reaction is reduced. The activation energy of the forward reaction is reduced to 35. The activation energy for the forward reaction is reduced to 35. What is the activation energy of the catalyzed reversed reaction? What is the activation energy of the catalyzed reverse reaction in kilojoules? Remember, we are told that this reaction, all this is uncatalyzed. But if it is catalyzed, the reverse reaction is from this end. The reverse reaction will be a distance from here. The activation energy of the reverse reaction is going to be reduced. For the forward reaction is reduced. If the forward reaction is reduced to 35, when a catalyst is used, the activation energy of the forward reaction is reduced to 35. Yes. So this will be 35. If a catalyst is reduced, this will be 35. So what is the activation energy of the catalyzed reverse reaction in kilojoules? Okay, remember that the catalyzed reaction will be a total of this and that. So the catalyzed reaction will be this. The reverse will be this, from here to this place. So it will be this and that. So the catalyzed reaction will be 190 plus 35, because we have been told the forward is reduced to 35. The activation energy. This is the activation energy for the forward reaction. Let me just show you something. Please. Let me show you something. This is a reaction. This is the activation energy for the forward reaction. Now, for the reverse reaction, the activation energy will start from here, right up. For the reverse reaction, the activation energy will start from here, right up. But in our equation, in our question, this one has been reduced to 35. So instead of 160, it is 35. So let's go back. So in this case, instead of, this is the activation energy for the forward reaction. This is the activation energy for the forward reaction. Instead of 160, it has been reduced. It has been reduced to 35. It has been reduced to 35. What is the activation energy of the catalyzed reverse reaction? So the catalyzed reverse reaction will involve 190 and the 35. Because it starts from here and up here to this level. This one has been reduced to 35. So the reverse reaction will be 190, which will be equals to 225. 225. So our answer here will be B. 225. Okay, question number 22. Question number 22 has to do with equilibrium constant. Equilibrium constant for the reaction. Equilibrium constant for the reaction. The equilibrium constant for the reaction, phosphorus trichloride with a gas plus chlorine will give phosphorus pentachloride, and this is 8.0 times 10 to the minus 3. The equilibrium, mole per dm cube, sorry. The equilibrium constant for the reverse reaction is, remember that the equilibrium constant for the reverse reaction is always 1 divided by the equilibrium, is always 1 divided by the equilibrium constant. It's usually 1 divided by it. If you have not, it is usually 1 divided by it. If you have not done it, so the equilibrium constant for this will be I think yes, the equilibrium constant for this is Kc. Kc is equals to 8.0 times 10 to the minus 3 per mole dm cube. Per mole dm cube. Now, for the reverse, Reverse, I can put reverse as K. K prime is the same thing. K prime C will be equals to, reverse will be 1 divided by 8.0 times 10 to the minus 3 per mole dm cube, and that will give us, it will give us this one, this will be equals to 1.25 times 10 to the second power mole per dm cube, mole per dm cube. That is the equilibrium constant for the reverse reaction. 1.25 times 10 to the power. Okay, let's see if we have the same answer here. Okay, so my answer for question number 22 is D. That is it. Okay, question number 23. Which of the compounds will give an alkane when reacted with soda lime? Soda lime, the role of soda lime in any reaction is to absorb the carbon dioxide and water that is produced by the carboxylic acid group. Okay, which of the compounds here have a carboxylic acid? It is only B. And soda lime, as I earlier said, it is used to absorb the carbon dioxide that is produced and the water that is produced by the carboxylic acid group. This is the only B is the only compound that has the carboxylic acid group that can do that. So B is our answer. Question number 24. 24. What is the general name given to the following reaction? The reaction here is phenylamine. Phenylamine is reacting here with this compound here, and they are asking us whether it is reduction, nitration, diazotization, and coupling. Let me write the equation, and you will see it well, and you will know the answer yourself. Okay, when sodium nitrite will react with acid, hydrochloric acid, what we will have is this is usually nitric 3 acid, nitric 3 acid, and sodium chloride. Now, the nitric 3 acid, now we will now react it again. We will take it and now react it with the phenylamine. Now, with the phenylamine here, what will happen will be that there is a salt that is formed here. There is a salt that is formed here. A salt with charges that is formed. And this salt, we call this salt a disonium salt. A disonium salt. It is very, very unstable. This salt is very, very unstable. That it removes. What happens is that it removes the hydrogen here. It removes the hydrogen and replaces it with the nitrogen. The nitrogen here. Remove the hydrogen here and replace with the nitrogen and the chloride. So the nitrogen goes and the formation of water. So because the salt is very, very unstable, the salt will decompose. This salt will decompose to do what? To give, the salt will decompose. Because I said, because the salt is very, very unstable, it will decompose on warming with water, because this salt when we warm this salt with water, this salt is very, very unstable, and on warming with water, it will decompose, giving off what? Giving off the nitrogen, and HCl, and a phenol is formed. A phenol is our final product that is being formed. Hydrogen is given off as gas, and HCl. Once more, this salt is very unstable. On warming with water, it will give off nitrogen, forming a phenol and HCl. So now our question is, what is the general name? Since it is the formation of disonium salt, we will now call it, we cannot call it a reduction, we can't call it nitration, we can't call it coupling, we will call it disotization. The formation of disonium. That is the formation of the disonium salt. Disotization. Okay, it takes us to question number 25. Question number 25. Question number 25 has to do with some oxides of the periodic table. Now, an oxide in period 3 reacts with sodium hydroxide and HCl to form salt. What is the formula of the oxide? Any oxide that will react with an acid and also react with a base, we call it an amphoteric oxide. And in that case, it is not carbon dioxide, it is not silicon dioxide, it is not beryllium oxide, it is aluminum oxide. So our answer is B. Our answer is B. Question number 26. Question number 26. Question number 26. A salt Z was dissolved in water. A salt Z was dissolved in water, and the solution gave a white precipitate with both sodium hydroxide and a silver nitrate. White precipitate with sodium hydroxide and silver nitrate. Yes. The metal present in Z gives an apple green color. Apple green color in a flame test. Identify the compound Z from the list below. Remember that this is a list, and only copper 2 chloride. Only copper 2 chloride will give an apple can give an apple green color. Only copper 2 chloride can give an apple green color. This is a color of a flame test of some salts. I said from only copper 2 chloride can give an apple green color. Then I said, and only copper ion are present, indicating the presence of copper ion. But now that we have been told that it has white precipitate, now we are now talking of what? A halide. We are now talking of a halide, a chloride. So now it cannot be C, it cannot be B, it can only be A, because only copper 2 ion gives an apple green color. Only copper 2 ion gives an apple green color. Lithium ion will give crimson. Sodium ion will give yellow. Potassium will give lilac. Calcium will give orange red. But copper 2 ion will give apple green. So in that case, our answer is A. 27. What is the partial vapor pressure of methanol in a mixture of methanol and the ethanol if the mole fraction of the ethanol is 0.8 and the total pressure of the mixture is 1 atmosphere? Okay, I will want you to. There is one thing I want us to do in this calculation. Remember that the total pressure, the total partial pressure of a mixture of methanol, total partial pressure is equal to the partial pressure of methanol and the partial pressure of ethanol. We will use that formula. We will use that formula. But we have been given the total partial pressure of we have been given the total partial pressure of the mixture. Now, to have the total partial pressure of ethanol, to have the partial pressure of ethanol, we have the mole fraction times the total pressure of the mixture. The partial pressure of ethanol is got by multiplying the mole fraction of ethanol times the total pressure. And the total pressure is what? The total pressure is 1 atmosphere. And the mole fraction of ethanol is what? The mole fraction of ethanol is 0.8. So now the partial pressure of ethanol is 0.8 atmosphere. The total pressure of ethanol is 0.1 atmosphere. Now we want to use the formula now again. Total partial pressure, or the total pressure, is equal to the partial pressure of methanol plus the partial pressure of ethanol. We now have the one for the mixture, and we now have the one for ethanol. We now have the total of the mixture, and we now have the partial pressure of what? Ethanol. So rearranging the equation, the partial pressure of methanol will be the one of the mixture minus the one for ethanol. If we do like that, we'll have 1 minus 0.08, which will be equal to 0.2 atmosphere, and that one will be our total pressure. It will be our partial pressure for methanol, and 0.02 in our answer column will be B. Okay, question number 28. The Avogadro constant is defined as the number of atoms in exactly 1 gram of carbon-12. No. What is Avogadro constant? Remember that the Avogadro constant is the number. The Avogadro constant is the number. This is the number of particles. The number of particles. I'm talking of ions, atoms, molecules, electrons. The number of particles present in 1 mole of any substance. The number of particles, that is ions, atoms, molecules, and electrons, present in 1 mole of any substance, and which is equal to 6.02 times 10 to the 23rd. So if it is not equal to 1 mole, then it is a wrong answer. Avogadro constant is defined as the number of atoms in exactly 1 gram of carbon-12. No, that is not 1 mole. B, the number of atoms in exactly 12 grams of carbon-12. Carbon-12 isotope is 1 mole. Carbon-12, 12 grams of carbon-12 isotope is 1 mole. Number of atoms in 112, no. Number the carbon atoms found in, no. So the only 1 mole here is the number of atoms in exactly 12 grams of carbon-12. That is carbon-12 isotope. So the right answer is B. 28 is B. Question number 29. What is the oxidation state of chlorine in HClO? Oxidation state of chlorine here, according to the rule in assigning oxidation number, this is a neutral molecule. Therefore, the total of the oxidation number here is equals to 0. So we will say it is H HCl O HCl O equals to 0. Remember that hydrogen is always 1. Is 1. We don't know plus chlorine. I don't know chlorine. Chlorine, let me say chlorine is equals to X. Oxygen is always negative 2. It is 1 and minus 1 is equals is X minus 1 equals to 0. X is equals to what? Plus 1. X is equals to plus 1. So it is A. Is A. Okay. 30. How are those two compounds? How are these two compounds? How are these two compounds? This is ethanol and methoxymethane. Ethanol, this is ethanol 1, 2, and methoxymethane related to each other. They have 1, 2, 1, 2 oxygen, 1, 2, 3, 4, 5, 6. All have they have the same molecular formula but different structures. So they are not they are not allotrope. They don't form. They are isomers. They are isomers. They are isomers. They are isomers. And what is differentiating them for purpose of revision? What is differentiating them is functional group isomerism. This is an ether. This is an ether. Methoxymethane is an ether, and ethanol is an alcohol. So it has an ether functional group. Meanwhile, ethanol has an alcohol functional group. So what is related between them is they are all isomers, but they are having but functional group isomerism. So the answer is D. 37. No, not 37. Let's go to 31. 31. Which reagent would be used to distinguish between methoxymethane and ether and ethanol? This is an aldehyde. Ethanol 1, 2. Ethanol is an aldehyde, and 1, 2, 3. 1, 2, 3. And propanone. This is propanone, yeah. This is propanone. This is propanone. This is propanone. Yeah. Ethanol and acetone. So, which reagent could be used to distinguish between a ketone and an aldehyde? It is not 2,4-dinitrophenyl hydrazine, no. It is to distinguish between them. Silver nitrate is a toluene reagent. Toluene reagent. So it is this reagent. This is a toluene reagent. We'll call it diamine silver 1 ion. This is a silver nitrate. The silver nitrate is a toluene reagent. Silver nitrate and this. We cannot use alkaline aqueous iodine because there is yellow precipitate will be formed here, will be formed in ethanol, and yellow precipitate will also be formed in this other one too. So we can't use this one. We cannot use this one because all of them will show the same color. So it is B. It is B, which is when we prepare this, we'll have a toluene reagent. A B will prepare a toluene reagent from B. 32. 32 is using the following half cell equation, the standard electrode, this. We have ion plus this to have this. Ion is, ion accept from the figures here, 0.77 volts shows that ion 3 is a beta oxidizing agent. Ion 3 is a beta oxidizing agent. For that purpose, ion 3 will accept electron and become reduced. It will accept electron and become reduced. Yes, it will accept electron and become reduced. Very good. D. Yeah, it accepts electron and become reduced here. That's good. In D. Then copper again. Copper 2. The value 0.34 volts shows that it is a beta reducing agent, which means that it will lose electron and become oxidized. Copper will be oxidized after losing electron. Will be oxidized. Will be oxidized. Will be oxidized from copper to copper 2. Yes, yeah, to copper 2. So D is our right answer. D is our right answer. 32D is our right answer. 33. 33. How many orbitals are there in a D subshell of an atom? A D subshell has a total of 10 electrons. And these 10 electrons are divided into 5 different orbitals. So they are altogether 5 orbitals. There are altogether 5 orbitals in a D subshell. So we have A as our answer. Now let's go to question number 34. Question number 34 says, which of the following aqueous mixture could constitute an acid buffer? Remember that for the purpose of revision, an acid buffer is a mixture of a weak acid plus the salt of that weak acid. A mixture of a weak acid and salt of the weak acid. It will give you an acid buffer. It will give you an acid buffer. Okay, let me use a weak acid here. Sodium ethanoate, then with sodium ethanoate and ethanoic acid. Yeah. So A is the right answer. A is the right answer. A is the right answer. 35. A is the right answer because that is what it is. Okay. Oh, now we have 35. Question 35. Which of the element with the electronic configuration given below will form an alkaline oxide? An alkaline oxide is an oxide of non-metal, especially group 1 metal. An alkaline oxide, that's a basic oxide. Basic oxide and alkaline oxide, one and the same thing, and usually of group 1 metal. And which of them here of the group 1 metal is not this one? S2 is no. S2, yeah, that is 8, 18, 19, and 19 is potassium. So D is the right answer. D is the right answer. Question number 35. Question number 36. Question number 36. The boiling point of water is higher. The boiling point of water is higher than that of methanol because remember that methanol and water, methanol remember that water can form, both of them can form hydrogen bonds. Methanol can form a hydrogen bond because it has an OH there. Water again can also form hydrogen bonds, but water again can form more hydrogen bonds because they can form more hydrogen bonds than methanol. Let's see what the answer is saying. The boiling point of water is higher than that of methanol because A, methyl group is electron donating. No. B, the molecular mass of methanol is more than that of water. No. C, the water molecule has more van der Waals forces than the methanol. Oh yeah, that one is acceptable if there is no any other better answer. D, water can form 2 hydrogen bonds per molecule while methanol can form only 1. D is the right answer. D is the right answer. Let's go to 37, 37, 37, 37, 37, 37. 37, 37, when boron trifluoride reacts with ammonia, the bond form is ionic. It cannot be ionic. Hydrogen bond, no. Dative covalent bond, simple covalent bond. Let me see. This is ammonia. This is ammonia. There is this is boron. Okay. There is a lone pair of electron here. There is a lone pair of electron here that can be donated here. In that case, I call this coordinate bond. I can now call this one coordinate covalent bond. Coordinate, I call this dative covalent, yeah. Dative covalent bond. So now our answer would definitely be C, dative covalent bond. It will be a dative covalent bond. Okay, which of the following compounds will exhibit geometric isomerism? Geometric isomerism. Which will undergo isomerism? You see this compound, the compound, this one cannot go geometric isomerism because they have two. See, which of the following compound will exhibit geometric isomerism? Two hydrogen here will not exhibit geometric isomerism. This on this one will not exhibit geometric isomerism. This one, two of these and two of these, they cannot exhibit geometric isomerism. There is hydrogen here, and there's hydrogen here, and there is the same group here, and there is the same group here. So D will exhibit geometric isomerism, cis and trans isomerism. So like in this case here, see here, this is trans isomerism. This is trans. This is trans, cis, and this we'll call this cis. This is cis isomer. This is trans isomer. Yeah, cis isomer and trans isomer. So and 39, the last section, which is 39, an acidified solution of potassium manganate 7 is changed to green on warming with propanone. On warming with propanone, it cannot work with propanone because it will only change to green when there is oxidation, when there's a reaction. These are alcohols. It will not react with propanone. It will react only with alcohol. So it can only change with propan 1 ol or propan 2 ol. So 2 and 3, 2 and 3 only. C. 39 is C. 39 is C. 39 is C. Yeah, which is 2 and 3. Okay, thank you. Thank you. I am very grateful. Fellow learners, thank you for watching. Please, before you go, please support us by liking the video and subscribing to our channel. Thank you.